In this video, we're going to be taking a look at optimization problems. So optimization problems are all about maximizing and minimizing some quantity that's specified in the problem that we're looking for. Now, when you're dealing with optimization problems, so it's a little bit different than something like related rates, where we need our equation to be in terms of one variable. We're not doing implicit differentiation of multiple variables. We need one variable here. So we're going to have to sometimes use secondary equations relating to the primary equation that we have, similar to related rates, but we need it so that we can get everything in terms of a single variable. So go ahead and you can read through these guidelines. They're also listed on your notes page. But we're going to work through some examples of optimization problems. So in this first example, we want to enclose a field with a fence. Our field is going to be rectangular. It's going to be a rectangular field. We have 500 feet of fencing, so that's important. And there's a building on one side of the field, so that side does not need fencing. So we want to determine the dimensions of the field that will enclose the largest area. So we want to enclose the largest area. So we're trying to maximize area here. So let's consider what all of our information is that we're given. So the 500 feet of fencing, what is this talking about? So generally when you put fencing on, you put fencing around the perimeter. So this is a perimeter, So this is a measurement of the perimeter. And we want to enclose the area. So we're going to have to find something to relate the perimeter and area. So let's go ahead and draw our figure here. So along one side, there's going to be a building. And then we're going to have our field here like this. That is going to be enclosed by the fencing and the building there. Okay. So we have our field. Now, because we're only enclosing 3 sides here, since we don't have to use fencing on this side, our perimeter equation is going to be slightly different. So if this is our length, we have width and width here. So normally the perimeter is twice the length plus twice the width, but since we're not enclosing this side, our perimeter is just going to be 1L plus 2W. And then the area, since it's a rectangle, is still length times width. It doesn't change just because we have that one side that's not being fenced. Now, what is it that we're trying to maximize? So we want to try and maximize the area. So we want to try and maximize this, which means we're going to have to try and get this in terms of a single variable. So we need to use our perimeter equation to try and rewrite it so that we can get rid of one of our variables here. And then in this, we're told that the perimeter is equal to 500 feet. So we can go ahead and use that information. And then let's go ahead and isolate L because it's the easiest to do here. And then we will substitute that back in here. So if I want to isolate L, this tells me that my length is going to equal 500 minus 2W. So I can go ahead and substitute this in for L to now have my area as a function of W. So my area as a function of W will be 500 minus 2W times W, which if we expand this out would be 500W minus 2W squared. All right. So when it says maximize means we're looking for, like, in this case, it's a quadratic. So that means we'd be looking for like the vertex. And we know that this happens when we have horizontal tangents, right? So if you think about relative extrema or absolute extrema, that happens when your derivative is 0. So we want to take the derivative of this. So what is A prime? So A prime of W is going to be 500 minus 4W here. And if you go ahead and solve this, you'll get that W is equal to, right, because we want to know when this is, solve it, when it's equal to 0, because that's when your derivative is 0, and that's when you have maximums or minimums. And so we have W equals 125 when you solve this equation. All right. Now, we have to also consider what's the possibilities for the length and the width in this, right? Because really, since we have a limited amount of space, there's only a certain amount of length and width that we could use to enclose this field. So we need the area to be positive. So in order for the area to be positive, this has to be greater than 0. And in order for this to be greater than 0, if you solve this, if you solve the inequality 500 W minus 2W squared is greater than or equal to 0, you'll get that W has to be between 0 and 250. Right? So the value of the width has to be somewhere between 0 and 250. And so when we try and determine whether or not W is a maximum or a minimum or whatnot, we have to look at treat it as if it was an absolute maximum, right? So we have to evaluate A at the end points of the interval and then also at our possible extreme value. So what is A of 0? What is A of 125? And then what is A of 250? Now, if we plug 0 in, right, so we're plugging it into this area formula here. If we plug 0 in, we can see that it's going to make this whole thing 0. Same with 250, right, because 2 times 250 is 500. 500 minus 500 is 0. Which means if this number here is positive, it is our absolute maximum. And so what is the value of A at 125? So that's going to end up being, if you plug it into your calculator, it's going to be 31,250. So that is the area, the maximum area, and the width that makes that true is 125 feet. So we know the width is 125 feet, and it's asking for the dimensions, so that means we also need to find the length. So we know that the length is 500 minus 2 times W. 2 times 125 is 250. 500 minus 250 is 250. So the length would be 250 feet. So those are the length and width that would maximize our area. Okay, example 2 asks us to construct a box with a square base. So this is important, right? It has a square base. And we only have 10 square meters of material to use to construct the box. We're assuming that all of the material is used, so we have to actually build a box in the construction process. Determine that what the maximum value is, or maximum volume, sorry, that we can have for the box. So what is the maximum volume? So we're trying to find the volume here. Okay, so telling us that it's a square base, so you can go ahead and draw your box. I did that beforehand. But telling us that it's a square base tells us that these two sides are the same, but it doesn't tell us anything about the height. So the height is variable. It's different from the dimensions of our base. So we'll just give it a different variable here, and we'll call it y. So you know when you find the volume, it's length times width times height. So the volume here is going to be x squared times y. Now, in this situation, we're also told that we have 10 square meters of material. So the 10 square meters of material are basically what we have to build the box itself. And so that represents the surface area. So what is the surface area? So the surface area, let's call surface area. So to find the surface area, we have to add the area of all of the faces of this box. So on this box, we have the bottom and the top. Those have the same area, and those are x squared. So we have 2 faces of that. And then all of the sides of the box have the same area as well. And those are all x times y, so base times height. And so we have 4 of those faces. So it's going to be plus 4xy. Now in this situation, we know that the surface area is 10 square meters. We're trying to maximize the volume. So we want to maximize this. So we need to try and use the surface area equation to get rid of one of our variables here. So let's go ahead and set this equal to 10. Because it's a y that's by itself here, I think we probably want to try and isolate y. Also because the y only occurs once, I think it's going to be easier to isolate y in this situation. So if I subtract 2x squared from both sides, I get 4xy equals 10 minus 2x squared. Divide by 4xy, we get that y equals 10 minus 2x squared divided by 4x. And then we can simplify everything by a factor of 2. So we have 5 minus x squared all over 2x. This is y. So we can go ahead and plug that back in to our volume equation to figure out what the new volume would be. So this tells me then that the volume as a function of x is going to be, so x squared times this, so it's x squared times 5 minus x squared all over 2x. So we see that one of these x's cancel, right? This is going to cancel with one of these. And then if I distribute this through, what I'm going to get is 5x minus x cubed, 5x minus x cubed all over 2. So that's the volume as a function of x, which we want to try and maximize. Now we know that our volume needs to be positive. And so it has to be greater than or equal to, or it has to be greater than 0. So to figure out the possible values for x, we could set this, make this x be greater than or equal to 0, because we know that it has to be positive, and then go and solve. So this is going to be 0 when the numerator is 0. So if I factor this, I have x times 5 minus x squared. And this is going to be 0 at 0, or it's going to be 0 at plus or minus square root of 5, right? So if this is going to be equal to 0 at 0 and plus or minus rad 5. So x equals 0 and x equals plus or minus the square root of 5. Now, clearly the length can't be negative, so that means that it's going to have to be between 0 and the square root of 5. So that's our feasible domain. So x is going to have to be between 0 and the square root of 5 in doing this problem. Okay, so that's our domain that we have to look and consider when we're trying to maximize this. So let's go ahead and go through the process of maximizing. So we're going to take the derivative of this here. So v prime of x is equal to, you can actually rewrite this as 5x over 2 minus x cubed over 2. I think it's going to make it easier to take the derivative. So the derivative is going to be 5 halves minus 3x squared over 2. And we want to know, where is this 0? So we can multiply everything by 2. So we're going to get 5 minus 3x squared equals 0. That tells me that 3x squared is equal to 5. So x squared is going, so x then would be the square root of 5/3. And it would be plus or minus, right? It would be plus or minus, except, again, we can't have a negative length here. So x is going to have to be 5/3. Now, if you test all of these values, right? So if you find the volume at 0, volume at square root of 5/3, and the volume at rad 5, right? Because we have to test whether this is absolute maximum or minimum. At 0 and at rad 5, we know that makes our volumes 0, right? That's how we found our domain. So those are 0, which means if this is positive, then that makes our volume the maximum here. So if you plug in the square root of 5/3 into the volume formula, you get 2.152. And that then would be our maximum volume. So it's going to be 2.152, and then it's meters, so it's going to be meters cubed. So 2.152 cubic meters is our maximum volume for this. All right, so in this third example, we have a cylinder. So again, I drew the cylinder already. It says a manufacturer needs to make a cylindrical can that will hold 1.5 liters of liquid. So we want to know the dimensions that will minimize the amount of material used in construction. So the amount of material used in construction, that's the surface area. The 1.5 liters, that's the volume. Now, one thing to note is 1 liter, because we can't use like a liquid measurement to talk about the materials used, but we can talk about an equivalent value. So 1 liter represents 1,000 cubic centimeters, right? So if you go back, think about chemistry, we know that 1 liter is 1,000 cubic centimeters. So that's going to help us. That means that 1.5 liters is 1,500 cubic centimeters. Okay, so what is the volume? So the volume of a cylinder is equal to the area of the base times the height. And the area of the base is just a circle, so it's pi r squared, and then times the height. So that's how you find the volume. We know that the surface area is just adding up all of the sides area. So we have 2 circles. We have a circle on top and a circle on bottom. So that's going to be 2 pi r squared. And then the area of the like outer part of the can is just going to be the circumference times the height. And we know the circumference is 2 pi r, and then the height is h. So it's going to be plus 2 pi r times h. Now, in this case, we're trying to minimize the surface area. So because the r's show up multiple times, we probably want to try and get rid of this h here. So we can set this equal to our volume that we know. So the volume is 1,500, and try and isolate h. So in doing this, we get that h would equal 1,500 divided by pi r squared. So we can go ahead and substitute this in for h here. So we get that the surface area is 2 pi r squared plus 2 pi r times 1,500 divided by pi r squared. So we can go ahead and do some simplifying. The pi's are going to cancel. This r will cancel with one of these r's. And then the 2 times the 1,500 is 3,000. So we get 2 pi r squared plus 3,000 divided by r. Okay. Now, you can see that we're going to want to minimize this, so we're going to need to take the derivative of it. However, what is the domain of r? Like, what are the possible values of r? Since we're trying to minimize this, that means that r can really kind of grow to be whatever measure we want as long as it's feasible, right? But the relationship between the radius and the height is inversely proportional. So as the radius grows bigger, the height gets smaller. So as r gets larger and larger and larger, this value of h gets smaller and smaller and smaller. So we know in this situation that r has to be positive, right? You can't have a negative radius, but also that it is not allowed to equal 0. So r has to be greater than 0, right? R has to be greater than 0. Okay. So if we were to take the derivative of this, I would rewrite this probably as 3,000 times r to the negative 1. So this is going to be equal to 2 pi r squared plus 3,000 times r to the negative first power, right? So this is the area as a function of the radius, the surface area. So if we want to take the derivative, so what is the derivative? A prime of r. So it's going to be 4 pi r minus, right, because it's going to be negative 1, minus 3,000 times r to the negative 2. So that just means it's going to be divided by r squared. And we want to know where is this 0. So before we can do that, we need to get a common denominator here. So we have to multiply this one by r squared on top and bottom. So we're going to get 4 pi r cubed minus 3,000 divided by r squared. Now, we want to know where this is 0. So we want to make the numerator 0. So if I make the numerator 0, if I go through the process of solving this, I'm going to get that r is equal to the cube root of this kind of crazy thing here, 3,000 divided by 4 pi. 3,000 divided by 4 pi. So that's what r would be. That number is going to be positive, so it's going to be greater than 0. And if we wanted to determine if it was in fact a maximum, you could do the second derivative test. The second derivative test will, or sorry, not a maximum, but a minimum. So the second derivative test, so we could take the derivative of this here. Again, I would probably think of this as 3,000 times r to the negative 2. So if we look at the second derivative, that's going to be 4 pi plus 6,000 times r to the negative 3, so it's going to be divided by r cubed. If I plug in a positive number here, this whole thing is going to be positive, right? So this is going to be greater than 0 for r equaling this, which tells me that this value is a minimum, right? Is a minimum by the second derivative test. So that value would be our minimum for the radius. And then for the height, you would just plug this in for r to figure out what the height would be. All right, so for this last example, we have a piece of cardboard that is 14 inches by 10 inches, so it's just like a flat piece of cardboard. But we want to make a box out of it, so we're going to cut the corners out. So they're cutting the corners out here, and here, and here, and here. So we're cutting out those corners, right, to give us now a box that has these little spots cut out, so we could then fold up the sides to make a box. So we want to know what is the height of the box that will give us the maximum volume. So we want to find the height that gives us the maximum volume. Now, luckily for us, we have this diagram here already, and it's already all in terms of h. Now, how did we get this information? Well, we know that this length here is 10. So if we cut out this little corner here, right, that's going to be, so the amount that we cut is basically going to be the height, because once we fold along this edge here, that measurement now represents the height when you've folded up your box. So since we cut the little square out of each corner, we have 2 h's there that are being subtracted from the full length of the box of 10. And then the same is true on the other side. So that gives us something like this. So when you're trying to find the volume, right, so when we're trying to find the volume here, we know that the volume is length times width times height. So that means that the volume is h times 14 minus 2h times 10 minus 2h. And if you expand all of this out, what you end up with is that we get 4h cubed minus 48h squared, and then plus 140h. So that's the equation for the volume as a function of h. Now, what is h, like what is the maximum height that we could have? So the maximum height that we could have, so h can only be between 0 and 5. 5 is the largest that the height could be. Now, how do I know that? Well, because this side is the smallest, right? Since I'm subtracting 2 times the height here, if I made the height 5, when I cut out my square, right? When I cut out my square, this would be 5, and this would be 5. So we can't actually have a height of 5, right? Because then we wouldn't have a side to fold up, right? It would just be, there would be nothing left here as far as for the width of that. So that 5 is going to be my maximum height, right? It can't be 5, so it has to be in between 0 and 5. So if I want to give the maximum volume, I need to take the derivative of this. So v prime of h is going to be, so that's 12h squared minus 96h plus 140. Now, if you try and factor this, you'll see that it's not factorable. So you have to go through the process of finding the zeros by doing the Pythagorean theorem. So if we set up this, right, equation here. If we want to find, because we want to find where it's 0, because that's when the where we have our relative maximums or minimums, right? When the derivative is 0. So if we go through that process and we do the Pythagorean, or sorry, the quadratic formula, if we do the quadratic formula, we get that the height is either 1.918 inches or 6.082 inches. Now, if you recall, we said the height had to be between 0 and 5 inches. So this one is not a possibility. So we need to test the volume of all of these different heights. So what is the volume at 0? What is the volume at 1.918? And what is the volume at 5? Now, the 2 on the outside are going to make my volume 0, right? Because if I plug 0 in here, that gives me 0. If I plug 5 in here, 10 minus 5 is 0. So the volumes on those ends are 0. And so at 1.918, what is my volume? So we can go ahead and plug this in. If it's something positive, you will see that you get a maximum there. So it's going to be 4 times 1.918 cubed minus 96 times 1.918. Sorry. 48 times 1.918 squared. Make sure you're plugging into the right formula. Plus 140 times 1.918. And we get 120.164. 120.164. So that is the volume. So since it's positive, that means that this value is the maximum. So this would be the maximum height. So this right here is the maximum height, or the height, sorry, that maximizes the volume.